sorry for being, I don't want to be between you and lunch, so I'll try to make this quick and sweet, and really looking forward to your thoughts on this project. First off, I want to thank the folks who organized this. I always enjoy coming to these meetings, and getting a chance to get up here and talk to you guys again is really great. So we're going to be looking at the role of soil moisture and how it impacts compound events. I want to give a shout out to Tyler Harrington and Kelly DePont. These were two students funded under this project who did some amazing work on various aspects. So moving right along with compound events. So we're going to transition from networks to do a little bit of research here. So compound events is a term that's being thrown around a lot more in the literature now. With climate change, we're expecting extreme events to increase in frequency, and the likelihood of these separate events we tend to think of separately, overlapping in space and time. It's going to become more frequent. And so compound events is the idea where you have maybe two extremes and they co-occur, creating worse conditions than if you had one extreme over the other. For this particular study, we're looking at droughts and heat waves. So droughts reduce the available water at the surface. Kosh had a really great slide yesterday showing the energy balance. When you reduce the amount of water available at the surface, you reduce ET, and this creates warmer temperature conditions. And then you try to superimpose that on a heat wave where you're already going to be hot. You can imagine things get worse. So we're going to be looking at how droughts modulate heat wave intensity, duration, and exposure. So we're going to be doing this using the U.S. Climate Reference Network. If you're unfamiliar with the network, I provided a map of where the stations are across the U.S. In the CONUS is where we have our soil moisture and temperature measurements. So we're going to be focusing on that. And that network really began in about 2009, but we have most of the U.S. covered by 2010 to 2022. So that's going to be our study period. We're going to be describing heat waves using hourly air temperature, and then we're computing a heat index. So we're taking our relative humidity measurements, combining it with temperature, and then computing a heat index. If you're unfamiliar with what that is, it's kind of like an apparent temperature. It gets at what your body feels in terms of, not just temperature. We found early on in our initial phase that we really need to be looking at this from an anomalous perspective. So for air temperature, heat index, as well as soil moisture and temperature, we're standardizing the data. We're computing a climatology and subtracting that climatology and dividing through by the interquartile range. So we'll get to that in just a minute. So the heat wave definition, we're going for a very basic one. We're looking at daily conditions. So we're going to be describing heat waves at an hourly level, but defining the start and end dates using daily maximum percentiles. And so 3 consecutive days above the 90th is when your heat wave begins. And then we do something a little different toward the end. We have a relaxation period. So if you have 2 days below the 90th, you could still, as long as your third day gets back up, the heat wave continues. And this allows us to get a little longer heat wave than just requiring the 3-day requirement. For droughts, instead of computing our own metrics at our stations, we went with US Drought Monitor. This is a well-known composite measure of drought that considers empirical information along with experts in the field. Some of the folks in the room provide input to the Drought Monitor authors. They synthesize all this information using a convergence of evidence approach. And so this allows us to, I'll go ahead and describe the range here. They categorize the drought data from none to D4, D4 being the worst category. We extract this at every station. We get a time series of weekly USDA conditions. And so for the definition, the first week you hit D1, drought begins, that's an event, and it ends the last week. You have 3 weeks in a row below D1. Okay, and so to define a compound event, basically, anytime you have a heat wave and a drought at a station at the same time, you're a compound event. If you have a heat wave and no drought, you're considered just a heat wave. So on this first graphic here, I'm showing you heat wave frequency. So on the your right, or my right, I guess your left. The heat waves is just the frequency there. This is the number of unique events we have. And then on the other side, we're showing you the difference. So compound minus heat waves. So positive values here, these are the orange and reds from California through Texas, where the bulk of those are. You have more compound events than you have heat waves. And the rest of the country, mostly, you have more heat waves than compound events. And so when we originally did our analysis, we didn't look at anomalies. We found that compound events tend to be warmer, but that's because they're in the warmer part of the country. So when we look at anomaly differences, so on the top, I'm showing you air temperature anomalies. And then on the bottom, I'm showing you the heat index anomalies. And we're just going to focus on the differences here. So in the top, compound minus heat waves, we see a lot of stations that don't have any color, which means there's literally no difference really between compound events and heat waves in terms of intensity. So this is your hourly anomalies, and you just average it over the heat wave event and subtract the two. For heat index, we do have a few more green stations indicating cooler conditions. And so you imagine if you're in a drought, you're reducing humidity, and that's going to bring your heat index down. So if you have water on your skin during a drought, it's easier to evaporate. So it kind of makes sense. You have a kind of a cooling protective effect, if you will. One of the interesting things, so that was kind of unexpected. One of the interesting things that we did find was when we looked at the duration of a heat wave. So this is the amount of time between the start and end date. And when we differenced that, we found that most of the stations are in orange color, meaning your heat wave is increasing with droughts. So the duration. So the maximum category there is 2 days. Our average heat wave event was about 4 days. So you're increasing that by about 1.2 or 1.5 times. So you increase the duration of a heat wave, and this leads to higher levels of exposure. So while you're not really changing the intensity, you do have more exposure because you have a longer lasting event. So here I'm showing you again, air temperature on the top and then the heat index on the bottom, where you're seeing the red stations. Apart from Washington and Oregon, it's really the 2/3 of the center of the country. So from mountain to mountains where you see a majority of the darker reds. And this is 30 degrees above the 90th on average over a compound event. That's the difference. You have 30 degrees more for a compound event than you do for a traditional heat wave. There is some mix. So you have stations where you have a large surplus in red and then also a large decrease in green there. So we're still trying to figure out why some stations go one way or the other. When we look at the heat index, the biggest impact is in the Intermountain West, so removed from the coast. These are areas where your humidity levels are going to be lower anyways in a typical heat wave. And so the droughts don't really provide a cooling effect in comparison. So one of the graphs that I really like here, this is showing you, because we looked at hourly data, we can compare the two metrics. So on the left here, I'm showing you temperature anomaly, and on the right, I'm showing you heat index anomaly. And you could do this by hour. And so what's interesting is that when you compare the temperature anomaly for compound events and the heat waves or no drought in this particular graphic, somewhere about 7 a.m. to about 3 p.m., there's no difference in the anomaly. But after 3 p.m., you start to see the heat wave anomalies begin to drop as you go later into the day. The compound events remain, so they don't cool as quickly. So where you do see greater levels of exposure during compound events is in the late afternoon to early evening hours. Then they reset as you go into the early morning. For the compound events, in terms of heat index, you tend to have lower levels of intensity again during the day whenever you're able to evaporate and generate that cooling effect. Because the drought monitor considers all aspects of drought, and it can tend to take a little bit longer to relax and onset, we decided to also look at this in terms of soil moisture. So in these graphs, we're taking all heat waves, regardless if they occur in a drought or not, and we're looking at what's the soil moisture conditions during those heat waves. So in this, for wet conditions, these are heat waves where our soil moisture conditions are 0.5 standard deviations or higher, so wetter, and then negative 0.5 or drier for the dry plots. And what's really interesting in this perspective, so the same kind of graph, air temperature anomalies on the left, heat index on the right. In the early morning hours, there's a big difference between wet conditions and dry conditions. So you're really cool. Your anomalies are a lot lower for dry conditions during the early morning hours. So this is the time, if you're going to be working outside during a compound event, this is where you want to be. When you go into the day, you actually see the slight bump, the reduction or the increase in sensible energy, where the dry conditions are slightly warmer than the wet or normal. And this continues through again, through the early evening and afternoon periods. For the heat index, we see that when you're wet, you're going to get higher levels of heat index for that particular metric, and that's consistent all day. And then, of course, when you're dry, you have lower levels. So to kind of summarize, we didn't really see much of an impact in terms of intensity, but it depends on the time of day. And one of the big things we did see is that when you have compounded events, the duration of the heat waves really increase, And this led to an overall average increase in intensity and exposure. However, the exposure picture was mixed. And we believe that's because when you have wet or dry soils, you can switch between states. So you imagine you're in a drought, you have some rain, it's not enough to end the drought, but maybe it's enough to moist the soils. And so this can create kind of feedbacks that you're not expecting, or when you just think about drought being dry all the time, maybe it's not from a soil nature perspective. So with that, I will yield the floor and let everyone have some lunch, and happy to hear your thoughts. Thank you.
Ronnie, we have time for a question if anybody's got one. I think. Don't think about lunch.
Do you take into account humidity as well when you do this, or are you just assuming it to be part of wetter and drier?
So humidity is rolled into the heat index. So we do have direct measurements of relative humidity. And so I didn't show the equation up here, but yeah. So yes, when you incorporate humidity, droughts have a protective effect.